Okay, so first part of this, the first lecture, we kind of went through the outline. Let's start recording now, because we're going to start the content of the course. So this course name is Finite Mathematics. So Finite Mathematics is a part of mathematics, is a branch of mathematics that deals with concepts and structures that kind of theories that does not involve infinite processes, such as calculus, right? So calculus variables can be very small or very big, and you have to deal with limits of variables going to infinity. So that's kind of what this course is not. This course, in the easier way, kind of to define, is a part of mathematics that deals with countable systems, things that are countable, and usually they involve set theory, combinatorics, combinations and permutations, probability, and a little bit of statistics. So that's what the course is about. We will start with sets, set theory. Then we will kind of go to combinatorics, where we will study counting strategies, how to count things. And this is the basics for probability that comes right after, and then also the basis for statistics. Okay, so let's talk about sets, right? So let's define sets. So a set is an unordered collection of objects. We usually use capital letters to denote sets. For instance, the set S or the set A. Okay. There are sets that have possibly zero or infinite many objects. Okay, although I said that finite mathematics don't cover nothing with infinity. There are sets that are that have infinity many objects. It won't be the kind of the focus of the course, but there are some sets that have infinity many objects, infinite many objects. Okay. So here are two examples that I want to show you. The first example is the set S. So again, a set is an unordered collection of objects. So we don't care about the order. Okay. So set S is, for example, composed of objects cat, of the word cat, dog, and fish. And usually we use this curly brackets here, curly delimitators here, to say that inside this set S we have this kinds of objects, okay, or this kinds of elements. So another example would be set A, right? That has elements C, letter A, letter N, and letter D. Okay, so I could show you the set, define the set A equal to C, A, and D, or I could give you a description of what I'm talking about, right? So I am talking about the set of letters in the word Canada. Okay. And again, this is an unordered collection of elements or objects. So it wouldn't make a difference if if we, so it wouldn't make a difference if this set was like A, C, N, and D, like with different order. Okay, the sets are the same because the order doesn't matter. Okay. All right, let me just go back to the format here. And oops. Oh God. And so that we can continue. Okay. Now, some sets are well known. And they kind of appear in the wild all the time. And there are sets that are less special, I would say. Okay. Some of the sets that are very common that appears in the wild, they have special names and special symbols to denote them. In this class, the most relevant set, like special set, is the one that has this symbol here, okay? And this symbol is the empty set symbol. It's kind of a circle with a line crossing it, with a diagonal line crossing it. And this stands for the unique set that has 0 elements in it, right? So this is what we call the empty set. So here we go. The empty set, you can see here, it has when you describe the set, you open the curly braces and there's nothing there. So it's called the empty set, meaning that the empty set has 0 elements. And so this symbol is reserved for this empty set, okay? Always. If you see the symbol, that's the meaning of the symbol, okay? There are also other special sets, right? For example, the natural numbers, the set of natural numbers. You will see this kind of stylished N. This stylished N here is also like a reserved symbol for this set. So when I'm going to describe this set is composed of 0, 1, 2, 3, 4, and dot, meaning that this continues forever. This is an example of an infinite set, okay? It's the set of what we call the natural numbers. Think about the number line. If we draw the number line, the natural numbers are starting from 0, the whole numbers, all the whole numbers that are positive. So 0, 1, 2, 3, 4, 5, this is the set of natural numbers up until, well, whatever number you're talking about. So this is an example of an infinite set, which is not kind of the focus of this course, but this stylished N is reserved for the set. The other set that you can find is the set of real numbers. It's a stylished R. And differently from the natural number, you cannot list or even give a clue using the curly braces notation, because the natural number set is you're giving a hint, right? You're stopping at 5 and you do dot dot dot. But for the reals, you cannot do that, right? So what is a real number? A real number is any decimal or fractional number. So you can have 0, 9, 8, 7, 1, 3, 2, meaning that you would be here. So you have all the fractions, all the possible in-betweens, the whole numbers here, okay? Including the negatives. Right, including the negative numbers. So, for example, minus 2.10. This is this number is part of the reals. Whole numbers are also part of the reals. So the reals are a bigger group, right? So 3 is part of the reals. But what I want to say is that I cannot kind of list all these numbers. There's so many little numbers, right? 0, 9, 7, 2, 3, 4, 5. And then 0.972355. So I cannot list these numbers in a good way. So I cannot kind of give this hint of the curly braces like the natural numbers. I have to use language, okay? And every set can be described with natural language. So for example, the reals, you will say reals, then you'll bring a comma, a column, and say set of real numbers. Okay, so it's an English description for a set of real numbers. You could also do that here, where you're saying, oh, this is the set of letters in the word Canada. We showed the set in curly braces, but we could also have described it with natural language, just using, there you go, A is the set, so you have the column and set of letters in the word Canada. Okay. As we talked about, most sets can be described with real language. Okay. For example, let's say that I want a set Q where I'm describing it with real language, that this is the set of all provinces in Canada. All right, so I can describe this with real language, but in this case, it's even easy to kind of list it, right? Because we don't have that much provinces, so it would be British Columbia, Ontario, Alberta, and all the rest. I'm not going to list it all, okay? I can also describe, for example, a set P, where I say the set of all Canadians who don't own a house. This is a description, right? Because in this case, I won't be able to list, right? I don't have a limited number of 10 or 12. I have millions of people, unfortunately, that don't want to own a house, right? So the best way to do it is just to use the language description. S, for example, this set here is the prime numbers between 10,000 and 100,000, right? So it's another way to describe, and it is and it's easier because it's very difficult to kind of list in curly brackets these numbers. Okay, they're too many. So one of the other things that we need to understand right now is that how to address what the elements inside of a set. So we use X is in S to say that object S is in the set of S. So this symbol here of it's kind of a stylished E. When you read this sentence, you're reading X is in, so this means is in the set S, or S is an element of the set S, okay? And similarly, Y is not, so the is not symbol is this stylished E with a line crossing it. So let's say that you have a set S, that X is an element and Y is not. So you can refer that with a more mathematical language using these symbols. I'll give you an example. Let's say that X stands for Ontario. I'm defining X as Ontario, and I'm defining Y as Michigan. Okay? So what can I do? What can I say about Michigan and Ontario? Well, imagine that Q, I'm working with the set Q, and we know that Q is the set of all provinces in Canada. So what can I say about these elements? Well, I can say that X is in Q, Because yes, Ontario is in the set of all provinces in Canada. So it is an element of Q. But now Y is not in Q because Michigan is not inside the set of all provinces in Canada. So this kinds of analysis, this is an analysis that will always have a element, and if it is in or not, a set, right? So we have this statement is always an element, is or not, is in or is not in a set. Okay, so in the right hand side we have a set, and in the left hand side we will always have an element. Okay, good. So now I want to also define what we call what we call a universal set. Okay, this is also an important definition, and the universal set is a set of all elements under consideration of a problem. Okay, and typically the universal set is denoted by U. So I'll give you a practical example. Let's say that I am considering I'm going to do an analysis on all the students in Western University. Okay, and so I'm going to draw a little bit of a little diagram here to kind of give us a little bit more of a heuristic. Say that this diagram here shows U. So U is U contains all students in the Western University. Okay. So what I have now, let's say that I have a set that is actually composed of students in math 1228. I have another set that is all the students in intro to developmental psychology. I have another set that are students in architectural design, and D, students in bridge design. Okay, so let's say that I want to kind of study all of these students. Okay, well, first of all, if I am considering all the students in Western University, this defines what we call a universal set, right? So all the elements that I am considering are inside this set. So for example, the students in Math 1228, well, they are Western students. Okay, they are all inside U. B, students into developmental psychology, they're all Western students as well. C, students in architectural design from the Faculty of Engineering, they're also in Western University students, and D as well. Okay, so this is my universal set. Now, this universal set means that anything that is under consideration is inside of it. So I will depict set A here as a little circle, meaning that this is the group of students in Math 1228. Okay, and I will depict group B or set B, students into developmental psychology, as also with a little circle. Now, this representation is very, very useful because we can see that some people that are, so for, let's say that Louisa is in Math 1228, and Simone is in developmental psychology. But there will be people that will kind of be inside both groups. Like, let me say Colin. Colin is a student in Math 1228 and in developmental psychology. Okay, so these kinds of representation are very nice, and we call them we call them Venn diagrams. Okay, we call them Venn diagrams, where you can represent inside of a universal set, right? You can represent all the sets that you are studying. Now let's depict group number C, or set letter C, set C. Set C are the students in architectural design. Well, I guess, and we can look at the data, but I would say that students in architectural design, they are further along the course, their program, so they already had Math 1228. So most chances are that C is not overlapping with A or B at any point, right? Because students in architectural design might have already taken Math 1228, and for sure they're not taking developmental psychology. Now I can depict also D, and now I'm overlapping them, because for sure some students in the engineering department, they are doing both bridge design and architectural design. Okay, so students here are inside both of the courses. Okay, so this is called Venn diagrams, and I'm depicting A, B, C, and D, but in the universal set, this kind of square, that embraces all of the other sets. Excuse me. So that embraces all of the other sets. You have more. You have lots of other groups, right? You have biology, medicine, but I'm depicting only the ones of interest. But all students in Western have to be inside this square. Okay? All right. If we have two sets, we also can compare the sets, this unordered collection of objects by asking, are any of the elements of A also in set B? Okay? So if all the elements of A are elements of B, we say that A is a subset of B. And we write A, this symbol here is a symbol for is contained in B. Okay? So let's try to understand some examples. First of all, let's say that I have a set composed by fish, and I want to compare this set that has only fish to this other set that has fish, cat, and dog. Okay? So this is the question. Are any elements of A also in set B? So given two sets, let's call this A, let's call this B. The question is, are any elements of A also in B? Well, there is fish. Actually, all elements of A, which is just composed by fish, but all elements of A are in B. So it is a subset, meaning that A is contained, in B. Okay? Or you can even put it this way. The set fish is contained in the set fish cat, and dog. Okay. Now let's play with another example. Let's say that I have another set, fish and human. Okay, and I want to compare. I want to know if this is a subset of this one: fish, cat, and dog. Okay, so well, actually, fish is part of the other set. So fish from this first set is also an element of B, right? Of the other set. But not all elements of A are elements of B. We are lacking human. Human is not part of the second set. So this is not totally contained. So again, you can write A is contained in B or is not contained by kind of crossing this diagonal line to the symbol. Okay? It is very, 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 very instructive to draw the Venn diagrams and understand a little bit better the concept of a subset or is contained, right? So given a universe, a universal set, I'm going to first write, and I'm doing this first example here. I'm gonna first write set A, which is, it contains only fish. So this is set A. And I will now write the other set, set B. Well, set B contains fish, cat, and dog. So in the end of the day, set B embraces set A. Or you think about it, A is totally contained inside set B. If this happens, then A is a subset of B. Okay? And you can write A is contained in B. Okay? So when we say that A is a subset of B, you have to have this image that all elements of A are inside B. So the whole set A is sitting inside B. Now let's do the second example. So inside our universal set, I will draw first so I'm here in this example. I'm gonna draw fish and human as set A. So set A contains fish and human, and set B contains fish, contains cat and dog. So this is set A and set B. Well, I cannot say that A is a subset of B because A is not totally contained in B, right? They have a common element, which is fish, but the whole set A, all elements of A should be inside B so that they are considered, so that A is considered a subset of B, okay? So just to clarify one thing, I want to kind of go back a little bit on the notation and say when we are comparing sets, this is totally contained or is a subset. You can read it both ways. And on the left-hand side, you need to have a set. And in the right-hand side, you need to have a set as well, because you're comparing sets, right? So the is subset or is totally contained is an analysis, right, between sets. So the left-hand side must be a set and the right-hand side must be a set as well. Okay, this is a bit different from the is element, right? Remember that we saw the is element. You have an element in the right hand side. So for example, we could say, well, fish is an element of set A. Okay, so this is element. In the left hand side, we have an element or an object, and in the right hand side we have a set, because this stylish E here is we're deriving a relationship between an element and a set. Okay, you cannot use A is element of B, because is element, the left hand side here needs to have a element and not a set. Okay, so I'm gonna do one more example, and here it is. So let's say that my animals, I'm calling set L, is fish, cat, dog, and Sarah's or Simone's animals, she has a fish and a crocodile. Okay, so we can draw the Venn diagram, and because crocodile is not in my set, right? You can see here through the Venn diagram that S is not totally inside L. So it would be if fish and crocodile were also my animals. So Louisa's set, but it's not. So to be a subset, to be totally contained, you need to have all elements of S sitting inside L. Okay? All right, so now we're going to discuss, some special properties, okay? No matter what set A is, it could be any set, we always have some particular truths. First of all, we have that the empty set is a subset of A, and A is a subset of itself. Okay, so this is a truth, two truths that are always valid for any set. Okay, so let's say that we have a set A, that it contains lobster, the words lobster, 100, and heart. Okay, so you can see that actually sets can have different objects, right? You don't need to have only words. You can have the word lobster, the number 100, and the symbol heart. Okay, it's just an ordered collection of objects. So what is this? Both these truths are saying is that A is always contained in A, right? So if you think about, I'm saying that lobster, 100, and heart, all elements of this lobster, 100, and heart are inside lobster, 100, and let me give myself some space. So lobster, excuse me, lobster, 100, and heart is all the elements of this first set is contained on the second set. And that's easy to see that's true, right? This is true. Remember, is totally contained. All this lobster 100 and heart set is it's actually the set itself, so it's kind of contained inside it. And the other truth is that the empty set is also a subset of A. Okay, So this one I won't, there's lots of proofs and beautiful ones. We're not going to go that way. It's a little bit advanced, but don't forget about the empty set being a subset of a set, right? So the empty set is nothing, right? No elements, and you have to consider that kind of having no elements can also fit inside another set. Okay. So when calculating subsets, remember, or when kind of listing subsets, given a set A is a subset of itself, and the empty set is also a subset of a given set. Okay. So if we have, and the other concept is if we have a universal set, all other sets that we're analyzing, no matter what, right? No matter what, they are subsets of the universal set, right? Because they stand entirely inside. They are contained by the universal set, and so they are a subset of the universal set. Okay. So let me talk now about the first operation that we have between sets, right? It's called union. So we can combine elements of two sets. Now, so we're going to do operations with sets. The same way we do operations with numbers, like 1 plus 2, or 1 plus 1 is 2. This is an operation, right? The sum, the addition is an operation, and you're operating into two numbers. We're going to operate into two sets, okay? We're going to operate into two sets. And the operation is between sets, and it's given, this operation is called union, and it's given by this signal here, the sign, the symbol, just as 1 plus 1, right? So you have number, the operation, number. Here you have set, the operation, and set, okay? And what does this operation do? Well, this operation combines elements from both sets and return a new set. So when we say 1 plus 1 is equal to 2, I'm doing an operation between two numbers, and I'm resulting in a new number. Okay? So for set operations, I'm operating in a set A and in two sets, set A and B, and this operation will result in a new set. Okay, so this is called the union operation, and this is a new set. Okay, and how does this operation works? Well, this operation works as this. A union B consists of every element that is in either A or B, possibly both. Okay, so let's say that we're creating this new set C by operating into this two sets, A and B, okay? This new set C will have every element of A or B or whatever is between in both of them, okay? And we're going to do an example to clarify this. But this operation is called the union of A and B. So let's say that you have a set A that is 1, heart, 3, and 5, okay? And let's say that you have a B that is lobster, tail, 10, 3, and 5, okay? So when I do this operation, when I'm doing A union B, I'm doing, I'm kind of making a mathematical operation. I'm taking A, I'm doing something with B to result in a new set. And the way it works, this operation works, is take every element that is in A or B, possibly both, or elements that are possibly in both of them. So I like to describe this operation as a hard copy, or the take-it-all concept. So the union is a hard copy of all elements in A. You're uniting, right? So all elements in A, 1, heart, 3, and 5. And all elements in B, lobster, tail, 10, 3, and 5. But look, 3 and 5 are sitting on both sets, right? So you don't need, because I already hard copied here, I don't need to repeat it, right? So I just finish here. So these objects are the result, this new set is the result of the union, the take it all, take everyone from A and everyone with B. Just be careful to not kind of hard copy the elements twice, the ones that kind of sits on both of them twice. Okay. So this is the union operation. Okay. There is a colloquial there's a colloquial word that is the colloquial word for this union operation. We say or. So sometimes you won't hear, oh, do an operation A union B. No, you will hear take elements of A or B, right? So it's kind of an English word for union. Every time you hear or, so take elements from A or B, it means that you're taking elements, and you're doing an operation of take elements from A or B, and whatever is on sitting on both of them. Okay. Finish this lecture by doing one exercise of a union operation. So I want to do an operation, so kind of come up with a new set that is formed by the union of A and B, right? So it's the I'm doing an operation, a union operation between A and B, or I'm taking elements from A or B. Okay, so remember about the colloquial word, right? First of all, the way I like to kind of state this is the take-it-all approach or the hard copy approach. So you will take everyone. You will take everyone that sits in A, so 1, 3, and 5, okay, and they're here, 1, 3, and 5. They're sitting inside A. And you'll also hard copy, take it all that are sitting in B. Okay, but just be aware that 5 was already, so you could hard copy 2, but you won't hard copy 5 again because 5 is here already. And the set is have unique objects here, so you don't repeat. So you hard copied A, 1, 3, 5, and you will hard copy B, 2, and 7, because 5 is already there. Okay? So this is what happened. 1, 2, 3, 5 came from set A. 2, 5, and 7 are from set B, but obviously I don't repeat 5, okay? Because I already copied. So B has 2 and 7, and A and B share this 5, okay? So what is the union? If you take a look at this Venn diagram here, the union is the take-it-all approach. So if I were to draw the resulting set, the set C, I would be drawing a big blob or a big circle that encompasses all elements of both sets. So this is set C. Okay, so it's take it all, take everyone. Take everyone from A and take everyone from B. Okay, everyone is in your team. Take it all. Okay, or hard copy everyone. And this is what the union is about. Okay, so I'm going to finish here and we're going to continue in the next lecture.